Alright, here we are for the last video of chapter 4.3. Chapter 4 is System of Equations. Chapter 4.3c, I guess chapter 4 System 4.3 is using the addition method. 4.3c is the last video of the addition method, and we're going to talk about what it looks like for no solution and what it looks like for the same line. So let's go through, here's our executive summary, I guess. Number one is make sure both equations are in the same format. That's going to be really important. Number two is clear fractions. If you don't want to work with those fractions, sometimes it's required for step number 3. Multiply one or both equations so that the coefficients of one variable, the number that's in front of the variable, are opposite. Positive 1, negative 1, positive 3, negative 3, so that when you add these up in step number 4, add up those modified equations to eliminate one of the variables. That variable that has the opposite coefficients will be eliminated. 5, 6, 7, 8 are just like the substitution method, where you have one remaining equation, it's got one variable, solve for the variable, give me a number, x equals some number, y equals some number. When you get that, go to step 6, substitute that value into one of the original equations, and then the result is an equation with just one variable, and solve that equation for the second variable and tell me what the other variable is equal to, and then you've got a solution and you can check. Alright, so there's the executive summary. We've done a couple of examples, and I guess what I want to do here is I'm going to stop here just for a second and say, let's see, what's our first step for this? Let's see, number one is make sure both equations are in the same format. Let's see, the red and the green equations, are they in the same format? Can we proceed? Let's see, are the x's on both sides of the equation? No. Up here, the x's are on the right side of the equation in red. In the green, x's are on the left side of the equation. So you'd have to modify that to move this over to the left side, move the x's over to the left side, and then you could proceed. So your first step would be just move this, take your 5y equals 7x plus 8, subtract 7x on the right, subtract 7x on the left, so you have negative 7x plus 5y equals 8, and that would be your next equation. You could say that this equation is negative 7x plus 5y equals 8, and then the green equation would be negative 4x minus 2y equals negative 10, and from there this shows this shows an example of making sure that both equations are in the same format. If you went here and said, well, 5y and 5, if you look at this and said, oh, I've got to clear out this column here and say that 5 times what is opposite of negative 4, you'd be making a mistake because you're trying to clear out, number one, y's and x's, and that's not correct. And you'd also be making a mistake because the x's have to be on the same side of the equation. So that's why you have to modify the red equation to make it this, and now these red equations, this red equation and green equation are now in a correct, I guess, method or format, so they can move forward, because the x's are on the left side in both equations, y's are on the left side in both equations, numbers are on the right side in both equations. Now you can move forward. But that's just an example of what I wanted to show you of how to make sure that each equation is in the same format. But the example that I wanted to do was one of these, because really we've done a couple of examples already using the addition method, and now we just really have to get comfortable choosing which variable to eliminate if we're going to use the addition method. So let's take a look at each of these systems, red and green, red and green, red and green. They're all color-coded for Christmas. If I look at this system of equations, my A system, I guess, which method, or I guess, what would I multiply the red and or the green to eliminate one of the variables? There's a couple different ways. What you could do is multiply the green by negative 2. So you could say I'm going to multiply the green by negative 2. When you multiply the green by negative 2, 17 times negative 2 is negative 34. And that would cancel out with a positive 34, and you'd carry on that way. You'd multiply all these terms by negative 2, and then you'd add your x's and y's and variables and eliminate the x. You could also choose, not incorrectly, and neither one of these are correct or incorrect, you could choose to multiply the red In a different scenario, you could choose to multiply the red by negative 4. And if you do that, then you'd multiply all terms in the red by negative 4, and this would be a different scenario from the multiplying the green by negative 2. Because if you multiplied the red by negative 4 and left the green alone, multiply that by negative 4 and multiply the y term by negative 4, that would give you a coefficient of positive 88 y for the y term, positive 88 and negative 88. When you don't modify the green equation, those y terms would cancel out, and you would also be able to move forward by multiplying the red one by negative 4. All right, if we've got, let's say, this B scenario, it's kind of a crummy little bracket there. If you got the B scenario, what would you do here? You could multiply the green, well, let's see. You could multiply the red by, let's see, how about negative 3? Multiply the red, let's see, I'm going to boo red. Multiply the red by negative 3. Why? Because if we multiply the red by negative 3, 15 times negative 3 is negative 45, and when you multiply all the terms and get a new red equation here, the green equation would stay the same, and the negative 45x would cancel with the positive 45x, and those would cancel out. Another possibility would be, instead of multiplying by negative 3 in the red, you could multiply by, let's say, how about positive 4 in the green? If you did that, 4 times 4y would give you positive 16y. And when you multiplied all these green terms out to get a new equation, the 16y over here would cancel with the negative 16y over there, and that would cancel out. You'd solve for x and move forward that way. Let's see, we'll do this in C. I'm not going to get to D, but I'm going to go to C right here. The C equation, or C system, is a little bit different because you'd have to multiply. Let's see, we've got fractions. I guess number one, is everything in the same format. X is on the left, yep. Y is on the left, yep. Numbers on the right, sounds good. So what would you multiply each one by? Let's see. I would probably choose to multiply in green, multiply to clear out the fractions. So I would multiply by, first of all, 4. So if we multiplied by 4, we'd go 4 times 1/2. 4 times 1/2 is 2x, minus 5/4 times 5 is 5y, equals 1. In the red equation, I would have 2x minus 5y equals 10. And you know what? Let's try to solve this, because now we've kind of moved forward with this one. This is a good example that we need to look at. Now what can we do? Let's see, we've got 2x, and 5y, and negative 5y. Well, you know what? Let's choose to attack the x's. Just multiply by negative 1. You can multiply the green one again by negative 1. So if we multiply by negative 1, this would give us negative 2x plus 10y, sorry, plus 5y. Yikes, hang on a second, let me erase that. Plus 5y equals negative 1. And now the red one has not changed at all. I've still got 2x minus 5y equals 10. And now we can use the addition method to add both of these up, because we're going to eliminate the x's. 2x minus 2x is 0. We don't write anything down there. 5 minus 5y plus 5y is 0. I guess on the left side we've got to have something. 0 equals 10 minus 1 is 9. Yikes, what happened there? Well, if we remember back to our substitution method, if you get something like this, 0 equals 9, that means that there's no solution. No solution. So before we actually jump to that conclusion, I would probably say, you know what, let's double check. Let's see, 2x minus 5y equals negative 10. 2x minus 5y equals 10. Sorry, positive 10. I'm going to double check that. I didn't modify that, but I did modify the green one by multiplying by 4. 1/2 times 4 is 2. Negative 5/4 times 4 is negative 5. Y equals 1. Sounds good. Oops, hang on a second. There's a mistake. 1 times 4 should be green. 4, I think it's not going to modify a whole lot here. If we multiply by -1, it should be -4. Alright, there we go. Now we can add 10 and -4 to get 0 equals positive 6. Yikes. Alright, but still, we still have no solution. Even though we double checked all of our work, 2x minus 5y equals 10 stayed the same. 2x times -1, -2x. -5y times -1, positive 5y. 4 times -1, -4. Add them up. 0 and 0 and 6. 0 equals 6. Still no solution. So we've double checked our work, and when we get to a solution, or when we get to an answer that says something like 0 equals -6, or 3 equals 10, or 15 equals 8, never going to happen, so that just means that there's no solution for the system of equations. So just like in our when we had solutions for the addition method, or sorry, for the substitution method, if we have parallel lines, which is the solution that we had before, we'll get something like 6 equals 12, or 0 equals 5, or 0 equals 6, like our example before, where the number is not equal, or the number is equal to some other number, means that this never happens, so therefore we have no solution. And those would be parallel lines. If we took a look at those lines back here, we could modify it to put it into y equals mx plus b format, and we would find that those are exactly the same slope, but a different y-intercept, just like in our section 4.2. By that same token, last point is, if we have the same line, in other words, if we've got the same y-intercept and the same slope, then we'll have something like 12 equals 12, or 0 equals 0. If we get something like this, that means that we've got the same line, and that means that our solution is the line, an infinite number of solutions, because those lines are both the same, so therefore the solution is the line. And you say y equals, my solution is y equals mx plus b, whatever numbers you've got for slope, and whatever numbers you've got for the y-intercept from the line. And that would be our solution, just like in 4.2.